Today we'll be discussing knowledge, and more specifically how knowledge and information is organized and stored in long-term memory. To put things into perspective, a couple chapters ago we talked about encoding, or getting information into long-term memory, and we also talked about retrieval, getting information out of long-term memory. So today we're going to talk about the middle step of storage, associating new information with information already stored in memory. In other words, we're going to be talking about how information is kept or arranged in long-term memory. Let me emphasize that specifically we're going to be talking about the storage of semantic memories in this chapter. Remember, semantic memory is your general knowledge of the world, the information you know about the Civil War, your knowledge of the features of different animals, the dictionary definition of words you know, etc. So we're not talking about episodic memories of events in your life or procedural memories of how to perform skills, just the storage of information regarding your general knowledge about the world. I always begin this topic with a little demonstration in my face-to-face class. What I do is to ask students to tell me what are the first three words that come to mind when you think of the following words. The idea is that this activity will tell us something about memory storage. The first words that come to mind for you will presumably be the words or concepts that are stored close to these words in your semantic memory. Anyway, here are the words, so write down the first three words that come to mind when you think of the word doctor. And now write down the first three words that come to mind when you think of the word movie. So once everyone is done, I say something like, well, it seems pretty obvious to me that semantic memory is organized like a dictionary. That is, knowledge is organized alphabetically. So I'm guessing the words you came up with were words that were alphabetically close to doctor, like docket, doctrine, and document. At this point, I look around the room, and of course, everyone is looking concerned because no one came up with these words, and I'm assuming you didn't either. So then I look concerned and say something like, okay, well, what about for movie? Did you come up with words that were alphabetically close to movie, like month, movement, and mucus? And of course, no one, including you, came up with words like these. So then I ask, okay, well, what words did you think of? For doctor, people give me words like nurse, hospital, and emergency. And for movie, it's words like film, theater, and actor. So then I go, oh, okay, well, yeah, so this does tell us something about the organization of semantic memory. Specifically, that it's not organized alphabetically like a dictionary, but instead it's organized semantically, or based on meaning and associations. To get more formal then, what we're going to talk about today are semantic networks, which are models that describe how semantic memories are stored and organized in the brain. Like we saw with the demonstration, the models will generally predict that concepts with similar meanings are stored close together and connected to each other. That is, long-term memory is organized by meaning. The models will just differ in their specific predictions of how information is organized, but again, all of them will say that it's based on meaning. Let me begin by introducing a couple important terms using some examples. So we're going to look at a simple semantic network, which again is meant to explain how information is stored in your brain, and specifically we'll look at your concept and knowledge of Frostburg State University. As we got through saying, these models predict that concepts that are associated or meaningfully connected to each other are stored close together. So you FSU psychology majors will probably have your concept of psychology stored close to your concept of Frostburg State University. We are going to call these concepts nodes. Moreover, not only are semantically related nodes predicted to be stored close together, but they are also predicted to be connected to each other. And we are going to call these connections associative links. Let's next fill out your semantic network some more. So what else do you know about Frostburg State University? Well, you know that the mascot is the bobcat, so your concept or node of bobcat will be stored close to Frostburg State University and connected with an associative link. And note that different people with different knowledge sets will have different semantic networks. Because my students attend Frostburg State University at the campus in Hagerstown, their concept of Hagerstown is connected to FSU as well. But for you guys at the main FSU campus, you wouldn't have an associative link between these nodes because you don't attend FSU at the Hagerstown campus. You don't associate Hagerstown with Frostburg State University. Similarly, a lot of nursing students take this course, and you nursing students probably wouldn't have an associative link connecting FSU and psychology because for you these terms probably aren't meaningfully related to each other. Instead, you would have a connection between FSU and nursing. And finally, let me make the point that nodes that aren't associated with each other will be far apart and not connected in your semantic network. For instance, nodes like Florida and Coast will be connected to each other because they are associated with each other, but they wouldn't be connected to Frostburg State University because we don't associate FSU with Florida or with the Coast. So now that we have a general idea of what the terms node and associative link mean, let's formally define them. A node is the representation of a concept or piece of information in a semantic network. To give you another example, here's what your semantic network surrounding the node doctor might look like. It's near nodes like nurse, operation, and hospital, nodes that are associated with the concept of doctor. As we mentioned, associated nodes are connected to each other by associative links, which are the connections between related nodes in a semantic network. So doctor is connected to nurse, operation, and hospital, which is then connected to ambulance by an associative link. Note that none of these nodes are connected to leaf, as we don't associate doctors or nurses or ambulances with leaves. There's one last new term I need to introduce, which is spreading activation. Spreading activation says when a node becomes activated, all nodes connected to it via an associative link also receive activation. Think of spreading activation like electricity flowing through wires. When you flip a switch and begin an electric current, the electricity will travel through any connected wire. That's kind of what spreading activation is like. When one node becomes activated, all nodes connected to it by associative links will receive activation and also become activated. Well, what does it mean then for a node to become activated? Well, a node becoming activated means that the concept enters one's awareness. So here's the idea. What happened during the activity when I told you to write down 3 words that came to mind when you thought of the word doctor? Well, your concept of doctor entered your awareness because I told you to think of the concept of doctor, so your node of doctor became activated in your semantic network. Then, what words came to mind? Well, it was those words that were associated with the concept of doctor, those words that were stored close to doctor in your semantic network, those nodes that are connected to doctor by associative links. The way we would describe this pattern in the model is that doctor became activated when I told you to think of it, and through spreading activation, this activation traveled out from the doctor node to connected nodes like hospital, nurse, and operation. When those nodes receive activation, they entered your awareness, which again is why you thought of those words when given the word doctor. Activation would continue to spread out to words like ambulance, and so you might have thought of words that were somewhat distantly connected to doctor for that reason. However, nodes that are far from doctor in your network, like leaf, don't receive any activation because they are so far away, and that's why you wouldn't think of words like leaf when I gave you the word doctor. The next topic I want to discuss on the PowerPoint is a very influential semantic network model that was created by Collins and Quillian. The model is discussed in the textbook, but I want to review the main features of the model, the study they conducted to test their model, and the results of that study on the PowerPoint because it can get pretty complicated. We'll begin by talking about the main features of their model. So the first key feature of Collins and Quillian's model is that nodes are arranged in a hierarchical order, from the most general categories at the top to more specific categories towards the bottom, and connected by associative links. So wow, there's a lot of information in that sentence. Let's begin at the top by discussing what categories are. So categories essentially refer to nouns. Here we see a small portion of the model. So we see the categories of animal, bird, fish, canary, robin, shark, and salmon. Notice that the categories, the nodes, are arranged hierarchically, with animal the most general category at the top, followed by bird and fish, which are types of animals below that, and followed by canary, robin, shark, and salmon below those, which are types of birds and types of fish. And finally, note how related categories are connected by associative links. So canary and robin are connected to bird by associative links because they are types of birds, but they aren't connected to the category of fish, well, because they aren't fish. The second key feature of their model is that categories and their properties are connected to each other by associative links. Again, this is a model of semantic memory, so the model represents or explains how we store our knowledge about the world. So let's fill in the model with the properties of the categories we looked at on the previous slide. In other words, what do we know about animals, birds, and salmon? The terms here that aren't bolded are examples of properties. Things like alive, eats, can swim, red, etc. Again, properties are what we know about categories. We know that animals are alive and that they eat. We know that birds can fly. And we know that canaries can sing. And again, properties related to a category are connected to it by associative links. Robins are red, but canaries aren't, so the property of red is connected to robin but not to canary. To get information about a node, then, you basically enter the model at that node and see the categories and properties it's connected to. So to access our semantic memory, to see what we know about fish, we enter the model at fish, and we see the properties that are connected to fish, that fish can swim. We can go up the model to see the type of category that fish are an example of, animals, and we can go down the model to see examples of types of fish that we know, sharks and salmon. The final key feature of their model is something known as cognitive economy, which says that properties are stored as high in the hierarchy as possible and apply to the category they are linked with and all or at least most categories below them. If we go back to our model, we saw that the property of alive is stored with animal and not with canary or shark or fish. Well, why is that? Aren't canaries and fish alive? Well, the idea is this saves space in the model. Instead of storing the property alive with every single type of animal you know of that is alive, it saves space to just store the property with animal and have that property applied to all categories, so all types of animals below it in the model. For another example, instead of storing the property can fly with each bird you can think of, let's just store the property can fly with the category bird and have that mean that all the categories below that node in the model, so all types of birds like canaries and robins, can fly. If we run into an exception, a type of bird that can't fly like penguins, we'll just store that property, that exception, with that category. Here's a larger view of the model. Notice in this example, the words in color are categories, and the words in black are the properties of those categories. Note the hierarchical arrangement of the categories. The most general categories like living thing is at the top, followed by examples of living things, plants, and animals. Notice how the properties are stored with categories. So the property has roots, for example, is stored with the category of plant. And notice how cognitive economy works in the model. We store the property has roots with plants because all plants have roots rather than storing the property with every plant we can think of, like trees and flowers and roses. After developing the model, Collins and Quillians conducted a study to test it. The idea is that their model is meant to simulate human semantic memory, so they wanted to see if their predictions turned out to be true, if humans behaved the way their model predicted they would. What they did was they tested their model by measuring reaction time for people to verify sentences about categories and properties as true or false. For example, they gave participants the sentences like a canary is an animal and a canary is a bird, and participants would have to respond true or false as quickly as possible, and their time to do so was recorded. Collins and Quillians' main prediction was that the time it should take people to verify sentences would be based on the distance between the nodes. The shorter the distance between the nodes, the faster subjects would be to verify the sentences. So let's look at the section of the model containing canary, bird, and animal. Specifically, we can see that canary and bird are one step away from each other in the model, while canary and animal are 2 steps away from each other in the model. So the prediction is that people would be faster to say yes to the sentence a canary is a bird than to the sentence a canary is an animal because the nodes of canary and bird are closer to each other in the model than the nodes of canary and animal. Other types of sentences participants would verify would be sentences like an ostrich has wings. So here you have a question or sentence about a category and a property. Other examples, a fish is a fish. And then there are false sentences as well, like a canary can swim. So what did Collins and Quillians find? The main result was that the closer two to-be-evaluated categories or properties were to each other, the faster participants were to respond to true. So here we see the reaction times for participants to respond yes to true sentences. Again, the closer the two nodes were to each other in the model, the faster participants were to say yes. This was true when participants evaluated sentences with two categories. So participants were faster to say yes to the sentence a canary is a bird than to the sentence a canary is an animal. And it was true when the sentence contained a category and a property. So participants were faster to say yes to the sentence a canary can sing versus the sentence a canary can fly. Remember, can sing would be stored with the category of canary because this is a unique property of canaries, while the property can fly would be stored with the category birds because all birds can fly. Anyway, I know this can get confusing, so please post any questions you have on the discussion board. Finally, let me say a little bit about feature comparison models of categorization. The textbook talks a lot about categorization or putting concepts into categories, such as looking at an object and determining that it is a type of chair, or looking at an object and determining that it is a type of vehicle, or a type of dog, etc. The textbook discusses different types of models for how humans categorize objects, specifically prototype and exemplar models, but I want to mention one more type on the PowerPoint, feature comparison models. The way feature comparison models say that humans categorize items is that concepts are stored in categories based on a comparison to a list of defining features. So for any category, according to this type of model, there is a list of features that define the items we would place into that category. All items in that category then have all of the features, and no item outside of the category has all of the features. For example, in order for a shape to be classified as a square, it must have the defining features of squarehood. That is, it must have four sides that are equal in length, that are straight, and that meet at 90-degree angles. In order for an object to be classified as a cat, it must meet the defining features of cathood. It must have four legs, be furry, like to chase mice, and meow when you poke it. I don't know. And again, an item belongs to a category according to this model if it contains the defining features of that category. To go over one last example, let's come up with the defining features for a bird, which would again be the features that an item must have to be categorized as a bird. So maybe the defining features are something like wings, beaks, feathers, and lays eggs for birds. So to decide whether to categorize an object as a bird, we simply have to check to see if it has all of the defining features. So robins, sparrows, parakeets, chickens, ducks, and penguins do have the defining features I mentioned, and so we would categorize them as birds. But bats, butterflies, and moths are missing one or more features, and so we don't categorize them as birds for that reason. Now, after talking about each type of model in the textbook, Goldstein discusses the main problem with that model. For feature comparison models, the main problem is that few categories can be defined by a set of defining features that satisfactorily describe all objects and only those objects in that category. So for example, what would you say are the defining features of chair? To come up with them on the spot for me, let's say the defining features are you can sit on it, that it won't break under the weight of one person, and that it provides some support for your body. Maybe you can think of a couple more features to add onto this list. The point, though, is that for whatever features we come up with, do these features actually encompass all of the objects that we would think of as chairs? That is, do all types of chairs we think of, kitchen chairs, rocking chairs, beanbag chairs, wheelchairs, etc., have all of these features? Moreover, do any items that we wouldn't categorize as a chair actually have all of these features? Well, for example, a rock would have all of the features of chairs that I mentioned. You can sit on a rock, it won't break under your weight, and it would provide support for your body, but humans normally wouldn't categorize rocks as chairs. So again, the problem with feature comparison models is that few categories can be defined by a set of defining features that satisfactorily describe all objects and only those objects in that category. So that's all I have for you today, but before I go, let me remind you all that your paper is due this week. The assignment instructions are posted on Blackboard, but if you have any questions about it, please let me know.